In this video, I'll explain a workflow for very high fidelity IC thermal modeling from the IC package level up to system level. A detailed IC package model is exported from Siemens EDA Calibre and imported into Simcenter Flotherm. The model contains a material map to represent the bottom end of line portion of the controller die. To incorporate this into a system level workflow, I'll export as an Embeddable BCI-ROM. Embeddable BCI-ROMs represent an automated approach to reduced order modeling that captures all of the thermal behavior of the IC and external boundary faces, but obfuscates all internal geometry and material data and is impossible to reverse engineer. It is an ideal technology to fulfill supply chain requirements from IC chip vendors to system-level integrators by enabling accurate 3D CFD thermal analysis. I then import and simulate the Embeddable BCI-ROM in a system-level smartphone model in Simcenter Flotherm. Material Map is a new smart part in Simcenter Flotherm 2404. Material Map is a computationally efficient method to represent the material variations for printed circuit boards, complex modern IC package substrates, and die metallization for accurate thermal analysis. To begin, I have opened the Simcenter Flotherm model created by Siemens EDA Calibre. The mold is shown as transparent for clarity. It contains two stacked memory ICs and the controller IC. The model includes 8 discrete heat sources, 1 on each memory chip and 6 on the controller. The controller BEOL is modeled as a material map with 19 layers at various thicknesses. Each layer contains material properties at a resolution of 1000 by 1000. To illustrate the detail included in the material map, we look at the Z conductivity for the M1 layer. The model has ambient or boundary condition faces predefined by Calibre, and the model is ready for export to Embeddable BCI-ROM. Source geometry and probe location are not selected, and the location will be obfuscated in the Embeddable BCI-ROM definition. The range of calibrated heat transfer coefficients and acceptable relative error are specified, and the model is exported. A system-level model of a smartphone is loaded into Simcenter Flotherm 2404. An Embeddable BCI-ROM is selected from the new object palette. The Embeddable BCI-ROM file is then selected. The model contains the geometry volume, face names, which are useful for positioning the part correctly in the model, the sources, and the probes, which are hidden based on the export settings. Source attributes are attached to each source in the Embeddable BCI-ROM, and the model is simulated. We look at the surface temperature plot of the Embeddable BCI-ROM to illustrate that this modeling approach not only accurately predicts the internal probe temperatures, but interacts with a CFD environment as a detailed IC package model would, and produces an accurate surface temperature gradient. A workflow for very high fidelity IC thermal modeling from the IC package level up to the system level has been shown. A ready-to-run detailed IC package model from a Siemens EDA Calibre that incorporates a material map for representing detailed material variation was imported into Simcenter Flotherm. An Embeddable BCI-ROM was created from the Calibre-based Simcenter Flotherm model and simulated in a Simcenter Flotherm system-level environment.